Today's lesson is binomial distribution, and this is actually extension of the Bernoulli distribution that we did previous lesson. So it still has all the characteristics of Bernoulli distribution because it's an extension of it. So we're looking at two outcomes, success and failure, and they are coming from running multiple Bernoulli trials. Let's have a look at the properties. There are four of them. The first one is the fixed number of trials. Second, of course, you'll get two outcomes, success and failure. Success is a P, failure is Q equals 1 minus P. And each trial is independent, which means you're going to get an equal chance. The result outcome is not relying on the previous trial. So, for example, without replacement, if you don't replace it, it'll affect the following trial. Okay, but if you keep replacing it, every event, every chance will be equal. And the last one is the probabilities are the same. Of course, if you got an equal chance, it's independent. You will have uniform. The binomial random variable is the number of successes from n Bernoulli trials. Example 6, state whether each random variable describes a binomial distribution. So we need to start think about that four properties. First one, the number of tails when tossing a coin 50 times. I can see that it's a fixed trial 50 times. So that's number one. I'll put that in there. And then tails. So we are picking certain things here. So tails, so that's our goal. That's our outcome. So it's either tail or no tail. So we got two outcomes. Number 3, independent. It is independent because it's not relying on any previous trial. And also each one has a 50-50 chance because tail, half chance, head, half chance. Okay, so that's all four properties. Happy with that. So therefore it is. And the second one, the number of red cards. Okay, so that's indication of the second properties. Two outcomes, red or no red. And then there's 8 cards, so it's a fixed. And the random is giving us the independence. It's not relying on a previous event. And also the last one is with replacement. So because you keep putting it back, you will have a same probability. So therefore, yes. But if it was a without replacement, there might be a bit of problem because it's not independent, because it's depending on what will happen on the previous event, and therefore no equal chance for each time. So no. Now, we can find the probability of all successes or all failures in multiple events in a binomial distribution. So what does that really mean? Let's have a look at the example 7. Find the probability of each event, leaving the answer in index form. Now, index form just indicates that it's multiple events, because it's keep happening. So your power goes bigger. Getting 10 heads when tossing a coin 10 times. Let's have a look at probability of getting a head is half. And then we're doing it for 10 times. So this is exactly what will happen. I'm just looking at right now here. Probability of getting 10 heads. So you're getting half probability for 10 times. So that will be half to the power of 10. That can be written as like that. Next one, getting 8 red cards when selecting 8 cards with replacement. Okay, so that's obviously binomial. At random from a bag of 10 red and 11 blue cards. Probability of getting red first, just one red. So to do that, we need sample space, which is the 10 plus 11, 21, and red is 10. So we're doing that for 8 times because we want 8 cards in an index form. You will get, okay. It is more difficult to find the number of ways of getting, say, 3 heads and 7 tails when tossing a coin 10 times. Yeah, obviously that's a lot involved in there. So it's going to be very difficult. Example 8. When tossing a coin twice, find the number of ways of tossing 2 heads. Start thinking about tree diagrams here. So we got 50-50 chance, same probability. So it'd be half-half to getting head and tail. And that's a first toss, and that's a second. Getting about 4 possible outcomes here. In that, we just want to know how many ways we can get 2 heads. There's only one way of getting 2 heads, which is head and head. So this is not finding a probability, just number of ways. All right, second one head. Okay, so we toss twice. So you're going to get head, tail, or tail and head. So there's only 2 ways you can have one head. Next one, 0 heads. That means both of times you're going to get tails. That's only one way. So that was just finding how many ways. Part B, when tossing a coin 3 times now, not twice, 3 times, find the number of ways of tossing 3 heads. Okay, so I've just sketched the tree diagram here. So the green color is the first time tossing, and the orange is the second, and blue is the third time. My possible outcomes, sample space, will be 8 of them. All have the same chance, equal chance of half for each. Head, half, tail, half. How many ways? 3 heads, there's still 1. Okay, so that's when you do it nicely. Now it's 2 heads. One of times it has to be tail. So how many ways? 3 ways. And 1 head, we got head, 1 head, and tail, tail, isn't it? So I will go tail, head, tail, 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 head. So I will get 3 as well for 1 head. 0 heads, oh, that's easy because that's just tail, tail, tail. That's just 1. So why are we finding how many ways? It's because we are about to use combination, permutations and combinations. I can see you guys going, no. Yep, it is. Let's have a look at Pascal's triangle because that's very useful. We know that and you can use it with the coins. So for example, if I pick this one first, it says 4 chooses 0. So that means that you got 4 coins and no heads. Okay, that was just 1 because they're all tails. In this case, 3 coins chooses 1 head. That will be 3 times because that's what we got here. Okay. And here, 2 coins chooses 2 heads. Okay, that's only 1. Just for fun, 5 coins chooses 4 heads. These are all the possible outcomes here. There are 5 of them, and if we can just put that in a calculator, you'll get 5. So this is another way we can think about. Well,
wait, sorry, Miss, I'm a bit confused. What do the numbers correspond to?
Pascal's triangle right there. It's got all the coefficients there. So this one is 1 coin with a 1 head. There's only one way you can get that. For example, here, you know that that's a 1, 2, that's a 4th. So it'd be 4 coins. 4 coins chooses 3 heads. So that's 3 ways. So they're just trying to use the Pascal triangles to find the outcomes of success. So probabilities in a binomial distribution. This sounds really complicated, but let's start with example. Say success is 20%. That's P. Failure is 80%, or you have to add up to 100%, and equals 1 minus P. Now I'm going to convert that to decimal. So my probability of success is 0.2. Probability of failure, 1 minus P, is 0.8. You have to add up to 1. Now the question is, find the probability of exactly 3 successes in 5 ways. Okay, so it's fixed trial. So let's have a look at possible outcomes. The first one will be, I'm getting 3 successes out of 5. So it'll be S, 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 and F, F. But that's not the only way. There will be a more. But let's have a look at the probability of that. Each success is 0.2. There are 3 of them. So it's 0.2 to the power of 3. And then failure, there's 2 of them. So I will go 0.8 squared. Then if I swap around the chances of success in a 5 ways, 5 trials, you will still have the same probability, wouldn't you? It'll be 3 successes and 2 failure. only thing that I have to times it is the number of the ways. Now we can say number of ways times 0.2 to the power of 3 times 0.8 squared. Now, what's 0.2 represent? It's a success, P, isn't it? And then 0.8 is failure, 1 minus P. So if I put that all in, I will go 5 chooses 3 because that will give us the number of ways. Okay, that's why we're doing combinations right now. And if you look at it, that chooses 3 is the same as the power of the success. And then the power of failure, 2, is the difference between the total trials and the 3 success. Now we can make a formula out of this. We can say NCR, where N chooses R, and then P to the power of R, which is the same as that, okay? And then 1 minus P, which is a failure, the difference of N minus R, and that will give us the probability. So that's what we got here. Okay, so NCR will give us the number of ways of getting success. So when you add the two powers together, 3 and 2, that's the total trial number. And also, what does that mean here? X in binomial, N and P. I just give you example on that. Say N is the total number of trials, and P here is the probability. Okay, so if I say find the probability of 5 tails with the 10 tosses of a coin. Okay, so my N is 10, isn't it? Because it's the 10 trials. And P is probability of getting tail, which is 0.5 or half. So you will write it like this. X binomial brackets 10, 0.5. Example 9. Hydrogen plant has a probability of 1/3 of producing white flowers. If 4 plants are grown, find the probability that only 1 plant will produce white flowers. What are we looking for? We're looking for the probability of getting 1 white plant. The success is getting a white one, and failure is not getting white. It's 1/3 is the success. We need to find out what is N, what is R. So N is the total trials, 4 of them. And we're just looking for 1. So how many ways will be N chooses R? So it'll be 4 chooses 1. This will change because it's R is now 1. So I will go 4, C, 1. P is a success, which is 1/3, and power of R, and that's power of 1. And then the failure is 2/3, and the difference between 4 and 1 is 3. But you can check that you're doing right with the power. When you add them together, it should be 4. The answer is, if you put it all in a calculator, you will get 32 over 81. Okay, so Maria tosses 8 coins. Okay, so that's our N. Now I can sort of straight away starting to see total trial we got. And to find the probability, yes, 5 heads. The head is our success. Coins is half. So how many ways? 8 chooses 5. 8 chooses 5. The success is half, is 5. It's 5 here. And the failure is half as well. And that's 8 take away 5, which is cube. And the answer is 7 over 32. Next one. See, if I roll 5 standard dice in a game of whatever that, and I find the probability that I roll 3 6s. Okay, so what is my N? 5 dice, and I want 3 6s. 6 is my success, so it's 1 over 6, and then not getting 6 is 5 over 6. I want 3 6s. 5 chooses 3. I mean, this one, you don't really need to do it. You can do it all in one go here. Success is 1/6, and that's a 3 here. And the failure is 5 over 6. The power is 5 take away 3 is 2. The answer is 125 over 3,888. Example 10. A certain type of machine in a car assembly plant has an average probability of 0.1 of breaking down. If the assembly plant has 8 of these machines, okay, so I can see my N right now. What is the probability corrected 3 decimal places? Now it's not fraction, it's decimal now. At least 6, okay, this is a tricky word. At least 6 will be in a good working order at any one time. So what does that at least means? Including 6 machines and then 7 and 8 machines. And then the probability of breaking is 0.1, not breaking is 0.9. We are getting good working ordered one, so 0.9 is our success. So just because 0.1 came up first doesn't mean it's a success. You have to look at the question at the end. What is our goal? What is our aim? What is our success? Success is getting the good working order machine. The probability of getting 6 machines working and then plus 7 machines plus 8 machines. So when you see that at least something, that it's inequalities. My total trials doesn't change, isn't it? Only 8 machines there. We want a probability of 6, probability of 7, probability of 8. That's what we want. And of course, the working is 0.9. Breaking, not working is 0.1. Concentration here. 8 chooses 6, 0.96, 0.12 plus 8 chooses 7, 0.97, 0.11. The last one, 8 chooses 8, 0.9 to the power of 8, 0.1 to the power of 0, because 8 take away 8 is 0. Okay, so one at a time. If you put all that in your calculator, you should have 0.962 into 3 decimal places. So that's all for today's lesson. Well done, people. Thanks.